Recall all or nothing secret sharing. It's a method to split a secret into two parts so that both parts are required to reconstruct the secret. So we could generalize this to split the secret among, say, 4 teaching assistants, TAs, so that only together they could all recover the secret. But any 3 of them would know nothing about the secret. However, it's risky to depend on all 4 TAs coming together at a scheduled meeting. So instead, we're going to search for a secret sharing scheme that's based on a threshold. That is, that any 3 TAs could jointly recover the secret, but any 2 TAs have no idea what the secret is. There are schemes that use fields other than GF2, but let's see if we can do it using GF2. So here's our first attempt. We select 5 3 vectors over GF2, A0, A1, A2, A3, and A4. A0 will play a special role. And these vectors have to be chosen to satisfy this requirement, that every set of 3 of them are linearly independent. To share a 1-bit secret S among the TAs, here's what I do. I randomly select a 3-vector U such that A0 times U equals that bit S. I keep U secret, but I compute these other dot products. Beta 1 is A1 times dotted with U. Beta 2 is A2 dotted with U. Beta 3 is A3 dotted with U. And beta 4 is A4 dotted with U. Then I give each of these bits to a TA. Beta 1 goes to TA1 and so on. I call those the TA's shares. Now, suppose 3 TAs want to come together and reconstruct the secret. Can they do it? Suppose, for example, the TAs 1 through 3 want to reconstruct the secret. What do? They solve the matrix vector equation, A times x equals B, where A is the matrix whose rows are the vectors A1, A2, A3, and the right-hand side B is the vector whose entries are the dot products beta 1, beta 2, and beta 3. Now, this matrix is square, and the rows are linearly independent by the requirement. So the matrix is invertible. So there's only one solution to this matrix vector equation, and it must be, therefore, this vector U, which we know is a solution. Once the TAs solve this matrix vector equation using the solver, they have U, and so they can reconstruct the secret S by just taking the dot product of A0 with the vector U. So we see that 3 TAs can reconstruct the secret. Now, suppose 2 TAs decide that they want the secret. They're not supposed to be able to construct the secret, but they've gone rogue. So TAs 1 and 2 know the bits beta 1 and beta 2. Can they use that to figure out the secret? We'll see that the answer is no. The information that they have is consistent with the secret bit being 0 and consistent with the secret bit being 1. Well, consider this matrix whose rows are A0, A1, and A2. This matrix is invertible by the requirement. So each of these 2 matrix equations has a solution, exactly one solution, in fact. I put 0 as the first entry in the right-hand side of the first equation and 1 as the first entry in the right-hand side of the second equation. The solution to the first equation is a vector v such that the dot product of A0 with v is 0. And the solution to the second equation is a vector v such that the dot product of A0 with v is 1. So the information that the 2 TAs have alone is consistent with the secret bit being 0 and with the secret bit being 1. So they don't learn the value of the secret bit. This scheme seems great. So what goes wrong? This scheme requires us to choose 5 3 vectors over GF2 that satisfy this requirement. And it turns out there are no such 5 vectors. So we have to do something a little bit more sophisticated. Instead, we're going to seek 10 6 vectors over GF2. A0, B0, A1, B1, and so on. And these form pairs. The first pair is A0 and B0. The second pair is A1 and B1, and so on. And the requirement that these vectors must satisfy is this, that for any 3 pairs, the corresponding 6 vectors are linearly independent. How would we use these vectors in secret sharing? To share 2 secret bits, S and T, I'll do the following. I'll choose a secret vector, U, such that A0 times U is the secret bit S, and B0 times U is the secret bit T. I give TA1 the 2 bits, beta 1, which is the dot product of A1 with U, and gamma 1, which is the dot product of B1 with U. Similarly, I give TA2 the 2 bits, beta 2, which is the dot product of A2 with U, and gamma 2, which is the dot product of B2 with U, and so on. So each TA has a pair of bits as that TA's share. Now, suppose 3 TAs want to get together and figure out the secret bits S and T. They set up a matrix vector equation that allows them to derive those bits. Suppose, for example, that TAs 1, 2, and 3 came together. They would solve this equation. They would put their pairs of vectors in to form this matrix and put the bits that they know in the right-hand side. Because of the requirement on these vectors, these 6 vectors are linearly independent. And therefore, this matrix is invertible so that there's exactly one solution to this matrix vector equation. That way, they can get the vector U and from that derive the secret bits. On the other hand, suppose TAs 1 and 2 go rogue and want to discover the secret on their own. They possess the bits, beta 1, gamma 1, beta 2, and gamma 2. Are these bits consistent with all the possible secrets? For example, are they consistent with S being 0 and T being 1? Well, they are if there's a vector that solves this equation, where I've put 0 and 1 as the first entries of the right-hand side. Now, since these vectors are linearly independent, there does exist a solution, exactly one solution. Similarly, no matter how you set these first 2 entries, there exists a solution. So that shows that the shares that the TAs 1 and 2 have don't tell them anything about the values of the secret bits. The secret remains safe.